And start recording, and I'll let people in as they come. So happy Monday, all. Rainy Monday. I'm going to start with the status sheet. I think Daniel Burns, I just got your SIPOC, right? I know you mentioned that. Daniel, you can hear me okay? This is the status sheet, so just basically, I'll just show it real quickly each week. Again, there's no urgency to getting everything done at once, but just kind of, I like everybody to try all the different tools. We got two more people, Stephanie and Mr. Hines. All right. So this is where I'm at. This is where we're at. Just, I'll just keep it running. We'll have this week. It'll be descriptive statistics to be the homework, and we'll just it's just kind of a way to, play along and do a little bit each week, and hopefully everybody will be all green by the time we're done. And with that, I'm going to start right into math practice to start. So homeworks have been Pareto, and then this week SIPOC, which is like most tools that we're gonna, a lot of the tools that we do, like root cause, affinity diagrams, SIPOC is no different than others, in that it's a group activity. It starts with makes it much more effective. You get much more information. It's very difficult to do by yourself. Josh, I loved your pizza making one. I think what I ended up with was I want to just show a couple. One is Ryan McNally. I don't know if Ryan's on. Yeah, but baby bath time, in terms of starting with the P, and you could actually take the steps of the process map and go list those process steps using the map, right? And then we go outputs. We go inputs and then suppliers, and then we work to outputs and customers. So in this case, baby bath time, gather supplies, fill the tub with warm water, undress baby, place baby in tub, play with baby so they don't start screaming, right, Bill? Wash baby, rinse baby, dry baby, apply lotion, get baby dressed, and then rest. And the outputs are clean baby, happy and calm baby, wet parents, dirty laundry, messy bathroom, the customers, mom and dad and baby. And then the inputs are buy lotion, buy soap, gathering all the supplies in order to do the process. And the suppliers are mom and dad, the baby store, and Walmart. I love it. And Michael Rochelo, see if I can move that over. He started with the process of a business process, which is really cool. Accept customer PO terms and conditions. So the process is customer POs received with the terms and conditions attached. And we review the customer folder for prior terms and conditions and or revision level change. If new or change, forward to finance, approve, red line for exceptions, and submit back to the customer, revise PO. There he comes. And approve as revised, and then file terms and conditions in the customer folder. So starting with that process map. And Michael, you want to take over? I just went through the P's.
Sorry about that.
No problem. So I just went through all the P's on your SIPOC. The outputs again are, for each step, if I do the process map being the P's, now we're into what are the outputs.
So again, what I hope I was able to portray was, inputs and outputs, and I got a couple places. So I struggled to whether there was exactly a
Michael, I think you, am I the only one that can't hear?
area and or. Oh, I lost you there, Bill. What's
You
going
did?
on?
Okay, let me grab it again. I'm sorry. Let me grab it back. How's now?
Yep, you got it
Everybody
back.
up? Yeah.
So again, as I was saying, where I believed I could absolutely quantify whether it was the external customer, was the supplier, and what their input was. Our team here, our customer service team, creating inputs, and then my team under finance team is a supplier, and then look to the outside to who got the resultant information, and what that information was. So that's how I determined what an output was and who the customer on the other end was the recipient.
I just love it because, I think you went through a lot of, in terms of, because when we use examples like feed the dog, baby bath time, we're just trying to get a sense of how this little tool works, and here, like, again, like so many of these tools, it makes it a lot easier if you have the process map to start, and then you have, the stakeholders in the process there, and it's just a 10,000-foot view of a process. So I think a really good job by everybody on the SIPOC. If you haven't tried it, give it a go. Either what Michael did or what Ryan did with baby bath time. I think Josh DeConti did making a pizza at home. But just to give you a sense of maybe, hey, there's something, it's in your toolbox, and there might be a time during the measure phase where you want to get a 10,000-foot view with a, either a swim lane map, value stream map, SIPOC, that kind of thing. So if you guys don't mind, I'm going to segue into today's topic as we continue in the measure phase, part 2. So we're going to get into some statistics today and some practice and some tools. So what I'm going to go through right now is basically the homework, right? What the homework going to be. So I'm going to ask you guys to do exactly what I'm going to do. What I'm going to show you how to do right now. And for those of you that it's a review, I apologize. What you're going to see over the course of this class is a lot of my weight data, because I've been every Friday I check my blood pressure, check my weight every Friday morning since January 27th of 2006. As you can see, my weight at that time, and I referee college football, so on TV I look like the Michelin Man. But basically, I realized I need to start monitoring my weight much closer. Plus, we have a family history of heart disease on my side. So I thought I had an aha moment in 2006 and said, all right, I'll weigh myself every day. On Friday, I'm going to do blood pressure and weight. My father had 9 stents in his heart before he died. So I realized I better collect some data, right? So as we get into the PowerPoint today, we're going to talk about descriptive statistics, right? And the value of them. I think the one theme over this course of the Greenbelt is data does not talk. It just lays there, right? It doesn't tell us anything. We have to make it talk. And that's kind of what descriptive statistics start to do. So what we have is 750 pieces of dates, Fridays, and just basically jumping on the scale and weighing myself. And I can go through and, and look at the data all I want, but it doesn't really say anything, right? So there's some graphical things that I can do to make the data talk. For example, if I highlight the date and the weight, and I insert a recommended chart, I could look at a scatter diagram, which is basically, it plots the date, and then each of these dots represents the weight. And you can kind of see some trend, some tendency of date versus my weight over 750 weeks. All right. I can do insert, recommended chart. I can look at just simply a line diagram, the same kind of thing, like a run chart. We're going to talk about that when we get to the PowerPoint, where it's date, it's one piece of data, and I can kind of see the tendency, the trend of my data over the last 750 weeks.
Can you look at it in season versus out of season?
Save that for the homework. That's exactly what we're going to get to, right? Because when we get, oh, you're way ahead of me, Michael. When we get into hypothesis testing, you know, one of the things you might say is, hey, you know, the null hypothesis might be Bill's weight does not change from winter and fall or summer and fall. And we're going to use this data to do some hypothesis testing. But right now, all we want to do is be able to make it talk a little bit, right? So that's kind of what the theme is today with descriptive statistics. So those are two simple charts that we're going to talk about when we get to the PowerPoint. And there's some other information here that's in yellow that I'm going to ask you guys to kind of repeat, right? So you can watch the video and kind of go through it. But, and again, I apologize to those of you like probably Ryan and Michael, you know, that are constantly in Excel all the time, you know, in what you do for a living, maybe Kyle. But for those of you who haven't used Excel for a while, or, you know, it's a review maybe, but here you go. So let's say out of 750, you got a nice scarf there. Looks so lifelike. What's my highest weight ever, right? And I can go through and look at the 750 pieces. This could be 10,000 pieces of data. It doesn't matter, right? All I have to do is hit to start any function in Excel is equal sign, and then start typing, in this case, max. And there it is, double click on it. I highlight my weight, hit enter, and I could see that the maximum weight that I ever weighed over the last 750 weeks is 199 pounds. And same thing with the minimum equals min. So equals starts it off, highlight my weight. Oh, sorry, apologize. Equals min, double click it, highlight my weight. There's the min. And I might want to know what's the min, what's the difference between the min and the max? How much range is there in my weight? And the easiest way to do that is just to simply equals the max. So highlight that, minus the min. And I can see that over the course of 750 weeks, my weight has ranged about 24 pounds. All right. And what's the average? The mean is the average. That might be important to know. And equals the av. And again, highlight the weight. And I can see that my average over the last 750 weeks is about 184 pounds. What do you think the mode is? Anybody? What's the mode?
Most common weight.
Yep, the one that occurs the most often, right? Again, equals starts it off. And most times there's mode right there. Highlight the weight. And most weeks on Friday, when I got on the scale, 186 was the most often. Okay. And the median, what do you think that is? Kyle, not you.
It's the number in the middle, but
Right.
not the
Right.
average.
So equals median. Highlight the weight. 185. That's the exact middle between all my data, 199 max, 175 low. The one right in the middle is the 185. And the standard deviation is simply what's the average away from that 184? Like what's the average variation away from 184? Okay. And when I do standard deviation, I get two options. You'll see standard deviation .p, standard deviation .s. This 750 weights that I recorded, is it a sample or is it the population?
Population?
Who said that? Yep, it's a population, right? Because it's basically, it's taking, because don't forget, my weight varies minute to minute, second to second, and I'd have to monitor all that. So I'm basically taking a sample and hoping that it represents what's really happening. Now think about it. When you guys see my pulse data in the next few weeks, my blood pressure, it's basically a process if you think about it, right? How I sleep, how I eat, how I exercise, all the things that I do, it's a way to measure, it's a measurement system for this process called Billy. So Billy hit it on the head. We're going to look at the standard deviation of a sample. So that's the second one down. So equals, double click, highlight my weight. And I could see that 4.189 is the standard deviation. What is the unit for that? What units is standard deviation in? Anybody want to take a guess? Is it kilograms? Is it
Same unit that your measurements are in.
Exactly. So it's 4 pounds, right? So in other words, the average variation away from the mean, 184 pounds, over the course of 750 samples, tests, is about 4.2 pounds. And now variance is important, especially when we get into some of the formula, when we get into hypothesis testing and stuff. It's basically the standard deviation squared. All right. And all that is same thing, variation, and it's asking me population or sample. And we're going to grab sample, grab the weight, and that's basically 4.18 squared, right? 17.55. We're going to use the variance is used in a lot of formulas instead of the standard deviation. And that's why we calculate it. It's part of the homework. And then the next thing we want to figure out is my data a normal curve? Is it normalized, right? Because when we get into the PowerPoint, once our processes are stable, then there's a lot of things that we can predict. Like we can predict future samples. So I want to know, is my weight data over 750 weighings a normal curve? And the way we do that is, first we have to determine a statistic called the Z distribution. And all we need to do to that is hit equals, then hit norm. See, norm dist is the first one, normal distribution, double click it. And then it asks me for a bunch of things. It says X, comma, mean, comma, standard deviation, comma, and then cumulative. So the X I'm going to use is that first piece of data, 194. And I'm going to put a comma in, space. Then see, mean got highlighted. Now I have the mean right here. It's 184.587. I'm going to put that there. And I'm going to put a $sign on either side of the F. Now I'll explain why in a sec. And then the next piece of information it's asked me for is standard deviation. And voila, by coincidence, we have that. And I'm going to put a $sign on both sides of the I and in between. And all that $sign does is when I drag the Z distribution down, it doesn't take, it always take F2 and I2. It won't take I3 and F3, I4 and F4, etc. It locks it. So I'm always going to get that absolute data from those cells. That's all the $sign does in Excel. And then the next question is it cumulative? And the answer is true. Hit enter. And there's my Z distribution. And then I just take the little corner and double click it. And it fills it in for all 750 pieces of data. And now I want to know if, I'm going to see if it's normalized by highlighting my date, hold the control button, grab the weight, and then grab the Z distribution. And then go in, insert, recommended charts. Uh-huh. Please hold. Hold on one sec. The back out. Oh, no, I didn't, I went too far. Let me go one more. There we go. Because I'm not gonna have you do this for homework, so I'm gonna make sure I got it, I don't make a mistake. The normal distribution, I'm gonna grab that, comma, mean, comma, standard deviation. Put the dollar signs in. I apologize. And standard deviation. You get to review it again, right? Dollar sign I2. I pressed true instead of false on the cumulative. That's why I didn't get what I wanted. And then double click. And then I'm going to highlight date, weight, Z distribution, and find out if my data is normal, which means it's a bell-shaped curve. Insert, recommended charts. How's that? So that's the Z distribution for my weight since 2006. The beautiful thing about a bell-shaped curve is it allows us to predict and answer a lot of questions. But I don't get a bell-shaped curve until my process is under control and I have enough samples. All right. For example, if I decide I want to understand the weights of every killer whale in the world, there's a certain number of killer whales I'm going to have to go catch and weigh before I get a normal curve. Because I may, in the first 10, 15 that I capture, I might have a whale that just ate, straight for 2 days, kale like crazy, or I got one that's dying, or so over time, there's a concept that we're going to get into in the PowerPoint called central limit theorem. And all it means is if I want to get to a bell-shaped curve, my process has to be under control, and it means go get more data. So this was not a bell-shaped curve if you think about it. When I started weighing myself in 2006, and as you can see, there's a high amount of variation in the data over the first 2 years. So if I had only looked at the data the first 2 years, I would not have had this beautiful bell-shaped curve. Now, if you look at the curve, the min, 175 pounds, is down the bottom left. The max, 199 pounds, is to the right. The mean at 184 is the center of the bell, right? So the object here is we want to continue to narrow the bell so there's less variation. And that's happened over the course of the last 750 weeks. At first, there was pretty good variation. And the game is, on all of our processes, when we talk about Six Sigma, is just to continuously drive out variation in the process. You also see that this is a Z distribution, close to a Z distribution. What a Z distribution is that my mean, my mode, and my median are pretty much on the same line, right? So the average, the one that occurs the most often, and the center of my data set is all right here. And it's pretty close, right? I got 184 for the mean, 186 for the mode, 100. So it's almost a true Z distribution. And then again, when I get into the PowerPoint, you'll see why it's so beautiful to have a bell-shaped curve, because I could do a lot of predicting, right? The percentages of data, and I don't want to confuse myself, so I'll wait till we get into the PowerPoint to explain the absolute beauty of a bell-shaped curve and why we want to, work to get our processes like this. So that'll be the homework. Basically, the way it'll go is, oops, sorry. This is what I'm going to send you. And I'm just asking you to do exactly that, just a little bit of practice, get the bell-shaped curve, send it back to me. And then to your dismay, next week, I'm going to show you how to do all that with like 3 clicks of the mouse, right? So, but this is, I think it's good to, for those of you guys that haven't done it in a while, or to review, and for the folks that haven't done it, it makes it pretty simple, okay? Any questions, descriptive statistics? We're beginning to make data talk. That's what we're doing, right? So we collect a lot of data, then it just lays on the page. It doesn't say anything. All right. So far, so good. Very excited about the math. All right, let's get into the PowerPoint. This will go fast, I think. I like doing, I just started doing this last class. I like doing the math first, you know, the math practice first, and then going into the PowerPoint, because I think it makes you go, okay, I got it, versus trying to go through this gibberish and then try to, you know, take it into the, I like doing it this way. So last week, we're in the measure phase. We've already defined our problem. And in the measure phase, what we're doing is we're saying, all right, how do we measure those vital few factors? What do we need to measure? How do we measure it? Our measuring systems work, the whole 9 yards. Last week we got process mapping, SciPoc mapping, some basic statistics and data collection. Today we're going to do descriptive statistics, central tendency, which is, you know, where's our average, what's our mode, some of the ones I showed you. Dispersion, which is how much is our data, how much does it vary? We'll talk a little bit about distribution normality, central limit theorem, and graphic analysis. And then next week we'll get into MSA, gauge R&R, precision and accuracy. And then next week we'll also do process capability, attribute and discrete capability, things like that. So anyway, without further ado, this is going to be a review now, right? So, so basically when we're looking at descriptive statistics, descriptive statistic describes what's going on. It's usually enumerative, includes organizing, summarizing, presenting data. If I had just shown you 750 pieces of data, it doesn't really tell you much, right? It's just a whole bunch of numbers all laid out on a page. And it also includes some of the charts that we just did. Box plot, we're going to go through what a box plot is. I'll show you how to do that. Pie charts, histograms, scatter diagrams, all that kind of stuff. Also in inferential statistics, when I do scatter diagrams, it also helps me make inferences about the data, right? And these are analytical statistics. It allows us to do predictions and draw conclusions. And the tools here are, and we're going to cover most of these in the analyze phase, hypothesis testing, a little bit more about scatter diagrams, etc. So it's basically all about making data talk, right? So descriptive statistics, it summarizes main features of the data. And when we talk about the data, we're talking about a sample, right? We're not going to take every piece off the machine and measure it. We're going to take a sample. We're going to have a sampling strategy, which we kind of talked about last time a little bit. We're going to get into more of it next week. But basically, what's the shape, the location, and the spread of the data? Okay. So let's start with central tendency, right? The location of the data describes the value where the data tend to cluster. And those are the average, the median, you know, the middle one, and the mode, which is the one that happens the most often. And here's the formula for a mean. I think before we had computers and Excel and all that, I think me and Michael, we had to do that with our slide rule. Exactly, right? Now it's like, wait till next week, like one click away. The median is the middle value. And if you have, you know, this is only a small set, it's kind of easy to see that 37 is, but if you had 2,000 pieces, well, it's still only a couple clicks away to understand what the median is. And the mode is the one that happens most often. So we could see easily here that 45 is. And then let's look at spread real quick, which we just did with the math practice. It's the degree of data dispersing around the center value, either the mean or the median. And there are multiple measurements to capture the spread. One is range, which is the difference between the min and the max. the variance and the standard deviation. The variance is nothing more than the standard deviation squared. So we can use that number in certain formulas. And we can skip this because we went through it on the math practice. And the variance measures how far on average that the data is spread out from the mean. And again, the game is, in Six Sigma is to constantly eliminate variation, right? It's this average squared deviation of each value from the mean, and which we can interpret to being 2 mouse clicks. And there's the formulation for the variance. So I have the differences between the individual data points and the mean, and I square that, sum that up, take my sample size, subtract 1, and that's my squared sample standard deviation. All right. And again, that translates to 2 mouse clicks. Standard deviation describes how far the data points are spread from the mean. It's simply the square root of the variance, and all data points are accounted for calculating the standard deviation. All right. And variation, again, is away from a target value. And it kind of indicates, it increases the chance that we're going to have a problem, whether it's going to get, our product or service is going to get rejected or not, whether it's going to get purchased or returned. It's the enemy of any quality process. And again, Six Sigma, a level of quality means that out of 1 million opportunities, we're only going to have 3.4 defects. Distribution and normality, we talked a little bit about that. That's the beautiful bell-shaped curve. It's a probability distribution of a continuous random variable whose values spread symmetrically around the mean. So symmetrically, it's equal on both sides of the mean, right? And luckily, over time, I've gotten my processes under control, and they're pretty predictable, and they're on equal distance on either side of the mean. Values spread symmetrically around the mean. That's the bell-shaped curve. The decent distribution is the simplest normal distribution. The mean's equal to 0, because don't forget, we did the weights, but I could also have 0 be the average, and then 1 standard deviation to the right, 2 standard deviations to the right, which would be about 4 pounds would be 1 standard deviation, 4 point whatever it was, 8 pounds, 12 pounds, 16 pounds. I can represent it that way too. On the one you're doing for your homework, you'll see that there won't be a 0 here. It'll be the average 184 pounds, right? And there's the formula to transfer a normal distribution to a Z distribution. That's the formula that we did, the box that we used, the last piece of data we calculated. And again, the normal distribution, the mean and the median, the mode is exactly pretty close to the same line, which we saw with my 750 weight values. But I could have a right skewed distribution depending on what goes into the process, those vital few factors. Y is a function of X. Well, the X's could be calories, it could be exercise, it could be hours sleep. There's a whole bunch of variables that go into that process, and it could skew one way or the other. But a normal distribution is where the mean, the median, the mode are right pretty central. Here's the beautiful part, guys, of the normal distribution is once I have a bell-shaped curve, and central limit theorem tells me that if I want to approach a bell-shaped curve, go get more data. Right? I don't have enough. All right. So I know that 68% of the data, once I have a bell-shaped curve, is going to fall within plus or minus 1 standard deviation of the mean. So that goes for my weight too. 68% of those 750 weighings are going to fall within 1 standard deviation. And I know that 95% of the data is going to fall between 2 standard deviations. So that's 8 pounds one way, 8 pounds the other way. So 95% of the data is going to fall within those in that spread. Okay. 99.7 is going to fall within plus or minus 3 standard deviations. And then almost 100 is going to be within 6 standard deviations of the mean. Yes, Michael.
Bill, when you use this in a practical application, do you assess, or is it, I guess this is the part of me as manager that says the cost to get me from 3 standard deviations to 2 standard deviations to 1 standard deviation exceeds the benefit? Is there times when that happens, that the pursuit of perfection is not worth it?
Yeah, I mean, if you look at y as a function of x's, you know, if you look at the individual x's, there may be times where you're like, well, it's just not worth being able to control those x's, that particular x, for whatever reason. I have to buy new equipment, I have to buy new measuring materials. I think the beauty of it is, let me get to this slide and then we can go back to that. Like, and what, so can I just put you out, like, just give me like a minute here and then we touch on that, Michael.
Sure.
So again, I know that if 68%, again, here's the number, 68% is going to fall within minus, then on either side of the mean, I'm going to have 34% of my data, right? And this is like, almost like Pareto. You know, when I have enough data, I know that on either side of my mean, 34% of my data is going to land. And when I have 2 sigmas, it's going to be 13.5 and then 2.35. And then now what do I do with that information? A quick little exercise, a little test here. The test scores of a physics class with 800 students are distributed normally. All right, so 800 means I probably have enough data to have a bell-shaped curve, right? I'm going to have an average of 75 on the test. And the standard deviation, if I do that, I find out that the standard deviation is 7 points. So in this case, I just drew a line from the mean, 75, and then each line is equal to 1 standard deviation of 7, right? 75 to 82, 82 to 89, 89 to 96, and the same thing with scores lower than 75, 68, 61, 54. So I'm going to ask a bunch of questions here. Based on the fact that this is a normal curve, I know that the average is 75. I know the standard deviation 7. What percentage of the class has a test score between 68 and 82?
%68%.
Correct. So I know it's 68% of 800 students are between 68 and 82. How many students have a test score between 61 and 89? So 61 and 89.
95.
How many students? Somebody other than Michael?
95%.
Right, if I add up all 13.5, 34, 34,
96.
I'll take that 800 and multiply it times 96%, and that's going to tell me how many students have a test score between 61 and 89. Now, what's the probability that a student chosen at random has a test score between 54 and 75? What's the probability in percent that a student chosen at random has a test score between 54, so 2.14%, 13.59%, 34 times 800 gives me that number, right? And then how many students have a test score greater than 96? And this may be, you know, in looking at my process and getting back to Michael's question, right? In terms of, I may want to do this because I want to know if the test that I've designed is fair. Is it doing what I want it to do? You know, am I failing too many? Do I need to put a curve on it? Things like that. And I think when you're looking at data like this, and I want to be able to influence the process, well, like Michael said, I mean, it's a business decision to say, well, you know, I think we're good. It comes back to the voice of the customer, right? And what are those things that the customer finds important? Are we hitting all those things?
I could make an argument here that the whether the test was fair or not isn't as relevant as the efficacy of the teacher.
Will you explain that? I'm sorry.
So if with that level of dispersion across that, how do you determine whether the test was the problem or how well the instructor taught was the problem?
Because there's such, I gotcha. Yep. But again, I mean, if I had those 800 test scores, you know, a graph like this helps us kind of get a sense of those types of questions. You know, it raises more questions. Any other questions, thoughts? I think the illustration here is that it's just, once you get to a stable process, there's a lot of things, a lot of questions that we can start to ask that we may not be able to ask by just looking at raw numbers. So there's a bunch of different types of distributions. Many processes have a normal distribution, but not all. Obviously, we can't have a phone call shorter than 0 seconds if we're looking at how long a customer service line, for example. You know, how much time are we taking to take orders, things like that. We're going to have a whole bunch of hypothesis tests, control charts that I'm going to show you that are all based on the first question is the data normal? And if the data is normal, then we're going to use this test, or this test for hypothesis, for example. And if it's not normal, then we're going to use another set of tests. So it's important to know. So I think the best way, the easiest way, you know, because there are ways to test normality. I think the simplest way is just what I showed you. Highlight the data, make a chart. You can get a sense if it's bell-shaped or not. And that's a normality test. And we're getting into p-value and alpha later when we get into analysis. So I'm going to skip through this. I don't think it does any, there's no value right now, I don't think, in trying to put this into your brain, because it doesn't help me at all. But central limit theory, again, states the sample size increases, data approaches a normal distribution. And there's a bunch of formulas that we're going to see when we get the hypothesis tests and control charts, you know, where the first question is the data normal? And second, is the sample size more than 30? Okay. And graphical analysis, again, we can go pretty quickly with this too. It's a method to visualize quantitative data, discover the structure and patterns in data, and a complete statistical analysis. You know, it's going to include both quantitative, you know, which is the mean, median, mode, standard deviation, all that, and graphical analysis. It helps the data talk off the page. And there's some common ones. We're going to go through box plot, histogram, scatter, run chart, dot plot. So box plot is a graphical method. I don't know if any of you guys have used this one, but it uses percentiles, and it uses medians of those percentiles. I think the example help make sense to it. It used to be called a cat and whisker chart. It's basically a box plot is, first step is, let's say I have a set of numbers at the top, 11, 22, 20, 14, 29, 8, etc., all the way across. First thing I do is put them in numerical order, ascending order from 8 to 49. And then down the bottom, I can draw a straight line from 0 to 50. And my box plot is going to sit on top of that line, where the right whisker will be at 49, because that's the biggest number. My left whisker is going to be at 8. And then the first thing I'm going to find is what's the median of all of this data. And that's where my Q2 is going to go. That line is going to be right at 20. And then I'm going to take the data from 8 to 20 and find the median there. And that's going to be my first quartile, Q1. And that's going to be at 12. You can see it's lined up with 12. And then I'm going to do the same thing with my data from 20 to 49. It's going to be the median's 28 here, so that's going to get plotted here. So basically, this is a line that kind of crosses 28. This one crosses 12. This one crosses the 20, which is the median of the whole sample. And then I just make a box out of it. And what is this? What do you think this tells you? You know, so my smallest number is 8. My biggest is 50. By looking at this box plot, what does it tell us?
Concentration of data.
Exactly. Simple as that. Histogram, graphical tool to present the distribution of data. Adjacent rectangles erected over intervals with heights equal to the frequency. Total area of all rectangles is 100. Scatter plot, which I think we did with the weight, represents a relationship between two variables of a data set. So we kind of did that with our weight, you know, for before. It helps us understand whether two variables are related to each other or not. What's the strength of the relationship, the density of it, what's the shape of the relationship, that kind of thing. And then a run chart, which I also did. This would be the weight and the date again. Present the data in time order. It captures process performance over time. And a dot plot's an alternative to the histogram if you want to see the frequency of individual values. And that's it. Wow, not bad. That's it. Not bad, right? So I'm going to send you math practice. And if you don't mind, just you know, practice. If you get stuck, you know, let me know. Yes, Michael.
Bill, on when you were graphing out your weight data, and we said population sample versus, or data was sample versus population, if you had selected population versus sample, does that yield a different result? I'm just.
No, I'm going to go ahead and do it, and I'll send it along with the homework. Maybe on another page, but it's pretty much the same.
It
Anything
would have a
else?
larger effect on a smaller sample set, right?
Yeah, there's a basically what it does is there's a correction in the formula when you look at sample, and we're going to see that when we get into the analyze phase. That if our sample isn't big enough, there's a correction that we can make, you know, where you're weighting less data different way. But I think in this case, because, you know, pretty much Z distribution, it's not going to make much difference. Anything else? Yeah, fun. We're done.
Thank you.
Hey, good to see you guys. I'll
Thanks,
get
Bill.
off right now with the recording. If you haven't done, if you haven't finished all the homework, please, if you get a chance, hop it off to me, all right? Is Craig Keller here finally? Well, Albrecht was off last week or something, Daniel?
Yeah, we had the week off.
Everybody?
I think so. Unless Craig chose to work.
All right, have a great night, guys. Thank you. Thank you, everybody.
Bye. Thank you.